So, Shivakumar, continuing on your question, I would suggest we go through this week 3 session first. Once we are done with that, in the spare time, we can look, uh,
Okay, sir.
into
That
the
uh,
week 2 question one. Fine.
yeah, okay, sir.
Okay, okay. Thank you. So, yeah, welcome everyone to the week 3 interactive session of the course Semiconductor Devices and Circuits, NPTEL NOC24 EE-143 tutorial. The schedule for the sessions is 5 p.m. to 7 p.m. And yeah, uh, this course is taught by instructor Professor Sanjeev Sambandan. Wait, I guess I forgot to switch on my video. Yeah, now fine. Again, let's quickly revisit the guidelines. In case you have any query, you can either raise your hand or you can just ask in the chat window. I'm fine with either of the things. And please make sure your microphones are muted, especially when you don't intend to speak or ask anything. And let's try to make this session as interactive as possible. And in that, I would appreciate your cooperation for the same. Uh, had stressed in the last session to keep pen and paper handy along with a calculator. And so I hope all of you would have done the same. So I expect answers in the chat today, if not over mic. And after this session is conducted, the session recording link and the lecture notes, they will be duly shared by the NPTEL course team and you can watch them. So I guess only 3 students have joined today. I wish to see more students joining in instead of watching the recorded sessions, because only then this session would be more interactive. Okay, coming to prerequisites now. The last week's lectures are the prerequisites for uh, this week 3 interactive session, which include topics such as density of states, Fermi function, carrier concentration, and doping. Okay, and I'm assuming all of you have already attempted the assignment 3 before tuning in to this week 3 live session. Fine. Let's briefly recap what was taught in the week 3 lectures. Right. We saw the concept of density of states, right? And we just a second, I'll use this. See, we saw the concept of density of states, right? And we saw, and in fact, we derived the expression for 3D material, 2D, 1D, and 0D. These are the expressions that we had obtained, right? The professor derived this in detail, so I need not go into depth. Then we also studied about the Fermi function, right? So the Fermi function actually gives the probability of finding an energy state at energy level E, right? That is occupied by an electron, right? And it's denoted by f of E and given by this expression, right? The E dependence. So uh, this is the plot of f of E versus E. F of E is on this x-axis and energy E is on the y-axis. Then this is how this carrier concentration varies with temperature, right? The freeze out zone, the extrinsic zone, and various other zones that were taught by professor. I'm sure you already would have gone through this as well, right? And then at last we have this relation, right? Can anybody tell me what this relation is? You can just type in the chat or just unmute and let me know. Simple question, right? This, right? Okay, I guess I'll answer it myself. So this is charge neutrality condition, right? Am I audible? Just confirm it once again.
Yes, sir, you are audible.
Fine, 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 fine. Thank you. So with that, we'll start with today's first question, right? Which is an intrinsic germanium wafer. It's doped with a shallow acceptor density of 3 Ni by 2, where this Ni is the intrinsic carrier concentration, right? At temperature T, all the acceptors, they are ionized, right? We are given some temperature T at which these acceptors are all ionized, and we need to calculate the hole density at temperature T, right? I'll just wait for a couple of minutes. Uh, and once you attempt it, just let me know, sir, we attempted, then I'll start showing it myself. Please attempt this question. Or we'll do one thing. Uh, I'll also start doing it and you can try this at your end as well. Okay, that will save us time. Okay, I guess I should insert a page. All right, done. So see what we have been given, right? See, we are given that this Na mines. What is this Na mines? 3 Ni by 2, right? So this is 3 Ni over 2. Now, since all acceptors, they are fully ionized, so we can use following thing, right? What we can write is something like this. Since all acceptors are fully ionized, so by charge neutrality condition, I can write N plus Na minus, that is equal to P plus Nd plus, right? Uh, which of the term is zero among these?
N minus P, ND plus. ND plus and N minus P. N
Okay,
is equal to P.
okay. I got your answer. See, Na minus is 3 Ni by 2, right? So this won't be zero, but this is zero, right? We only have this accepted doping, right? So we'll assume that this is zero, right? So let me then make this zero. I appreciate, please keep answering regardless of, I mean, if the answer is right or wrong. I'll really appreciate if you continue answering the questions. So now what we'll then write, we'll write that N plus Na minus, that is equal to P, right? So how should you proceed then? Keep in mind, we need to compute the hole density at temperature T, right? Okay, someone is typing, I guess I should wait. Using mass action law. Exactly, we need to use law of mass action, but to eliminate what? By law of mass action, I can either eliminate N or I can express, I mean, N in terms of P, right? And I square equal to NP. I agree, we need to use law of mass action, but should I express this in terms of N or this in terms of P? That is the question. Remember, we need to compute hole density. So what should we eliminate, right? We are interested in holes. So let's eliminate this. How we'll do that? As Shailendra pointed out, NP is Ni square. Eliminate N, yeah. So what we'll do is we'll write this as Ni squared by P plus Na minus is equal to P, right? So this implies this is given by If you multiply throughout by P and rearrange, this would be, just do it. You guys should have pen and paper, right? Just see if this comes about. It should be P square minus 3 by 2 Ni P minus Ni squared is equal to 0, which is a quadratic equation in what? This is quadratic in P, right? I mean, it's quadratic in Ni as well, but we are interested in P, right? Ni is something that is known. This is quadratic in P. So the solution is given by the high school formula. P is equal to minus this coefficient, right? So I should write, I'm assuming all of you know this, right? This is pretty trivial. 3 by 2 Ni plus square root of, I mean, I will only take the plus sign because mines actually won't be physical. You can just check that out. This would be b square. So this should be, wait, do one thing, just let me know if this is what you get. Do all agree that P should be given by this, or does somebody have a different opinion? I guess all agree, right? So I will continue. If at any point of time you don't agree, just type in chat that we don't understand and I'll explain that again. So this implies that P is equal to 3 by 2 plus, I'm taking an I common. So this should be, this is square root of 4 4s are 16, 16 plus 9 is 25, 25 by 4 square root, that is 5 over 2, right? So this would be Ni, and this is whole divided by 2. So which is nothing but, what should be P? Just work it out and let me know in the chat. Why aren't you guys responding today? This is simple, right? I mean, what is 3 by 2 plus 5 by 2? And divide that by 2. 2 Ni. Yes. So this is P is equal to 2 Ni. Done. So which actually finishes our question 1, because this is the right answer, right? This is C, that is 2 Ni. Now, question number 2. Okay. Please go through this question and attempt this. So the question is, under which condition the position of Fermi level in an intrinsic bulk semiconductor lies exactly at the middle of the band gap at non-zero temperature T? So what is the condition? I mean, it could be either of these 4 conditions. We just need to point out which one. When this position of Fermi level in an intrinsic bulk semiconductor lies exactly at the middle of the band gap, right? The intrinsic level, EI, it should coincide with EI. Obviously at a non-zero temperature T, because answer is D, when effective mass of electrons is equal to effective mass of holes. That is, I guess I will wait. Does someone disagree with the answer that Shailendra wrote? Shailendra says it's D, when effective mass of electrons is equal to effective mass of holes. Anyone else who wants to attempt this or answer this? No one? Okay, fine. So this answer is actually correct. Let's see how. So this is sort of a derivation based, I guess. So we know that Ni is equal to square root of NCNV exponential of minus Eg by kT. Actually 2 kT, right? Where this Eg is your band gap, right? If we take ln on both sides, we get following, right? We get ln of Ni, that is equal to ln of this square root of NCNV, right? Minus Eg over 2 kT. Fine. So this, let's denote this as our equation first. Then uh, for an intrinsic semiconductor, we have following, right? I guess I will use a different page now. For intrinsic semiconductor, Ni is given by this Nc exponential of, you all know this, right? Nc exponential of minus Ec minus EFI, where EFI is your intrinsic Fermi level, whole divided by kT, right? Everyone remembers this. Then if we take ln on both sides, we get following. So ln of Ni, that is equal to ln of Nc plus, actually minus, because this minus sign is there. This is minus Ec minus EFI by kT, right? Then what we can do is, if we rearrange, we get the following. We get kT, right? Ln of Ni minus ln of Nc plus Ec, that is equal to your EFI, right? You can just quickly verify this. This is simple mathematical jugglery. Then we can write this kT ln of square root of NCNV minus Eg by 2 kT minus ln of Nc, right? Plus Ec is equal to your EFI, right? What have I done? I use this, right? Instead of ln Ni, I use this ln of square root of NCNV minus Eg by K2, right? This is what I did. Rest of the things are same. I guess I will write so that you guys don't confuse. This is using first. Then let's continue. Then you can write this as minus KT ln of square root of NC by NV minus EG by 2 plus EC is equal to EFI. Okay, somebody is typing, I'll wait. Do you have any doubt, Shailendra? I'll just wait. Let him complete his query. So can we use EI is equal to EV plus EC by 2 plus 3 by 4 KT ln of that expression? Well, I mean, you can, but I mean, see, the point is to finally impose a condition using effective masses, right? Hole effective mass and electron effective mass. I mean, either way, you'll come to the same conclusion, right? That is, when the two effective masses are same, only then uh, the question condition that was imposed will be followed. Fine. So if you want, you can proceed like what you showed. See, now I'll use following. I know NC and NV have effective mass dependence, right? So what that dependence is actually, let me write the expressions. You should actually remember these as well because they might come handy in problems. 2 pi mn star kt by h squared 3 by 2, right? Similarly, what is NV? NV is 2 pi mh star kt by h squared, sorry, 3 by 2, where this mn star and mh star are electron and hole effective masses. Fine. Now what is Nc by Nv? All right, this ratio. That is Mn star by Mh star, whole raised power 3 by 2. Right? So now I'm using that. Fine, I'll use this here. I'll get following. I'll get this minus 3 by 4 kt ln of this is Mn star, right, by Mh star. Uh, or let me do one thing. Let me denote this by P, right? Since I'm not using E here, I'm using N. So let this be P for whole. This be P. Let this be P. Okay, I'm done. So then let me complete the expression. This is plus EC minus EG by 2. Uh, this one done, then EFI, right? This is your EFI. So then when this Mn star is equal to MP star, what will happen? When that happens, this will cancel out, right? And ln of 1 is 0, right? Assuming the base is finite. So this will be 0, right? Let me just write this. When Mn star is equal to MP star, right? Uh, this term goes to 0. I mean, by color notation, you would understand what I mean. So when that happens, our EF would be equal to EC minus EG by 2, which is nothing but intrinsic level, right? So this is what we needed to prove. We are done with this. Okay, regarding question 3, I initially, I mean, intended to show this in this session, but at the last minute, I realized this question is actually the one that has been asked in the current assignment. So that is why I would skip this one. Okay, actually, I'm skipping 3 questions that I initially intended to show. So we'll directly go to the question number 4. So the probability of a state being filled by an electron at energy EC minus KT is equal to the probability of a state being filled by a hole at energy EC minus 3 times KT. Where is the Fermi level located? A simple question, right? Just attempt it and let me know the position of the Fermi level. Please attempt this. And I'll also do the same. So it's given that probability of a state being filled by an electron at energy EC minus KT, right? That is 1 plus exponential of, let's uh, see, in general, there's the probability of a state being filled by an electron at energy some E, that is given by this expression, right? This should be exponential of E minus EF by KT. Uh, and what is the probability of a state being filled by an hole at energy some E? What is that expression? Let's write that. That is, let's denote that by, this is E, right? And this is H. That should be 1 by 1 plus exponential of, this is, okay, let me write EE to distinguish it, right? This would be EF minus EH by KT. So this is the state that is filled by an electron, and EH is the state that is filled by hole. Fine. So these two are done. Let's now solve this question, right? So now, as per the question, this EC is equal to EC minus KT. And what about EV? I mean, sorry, why am I writing EC? This is EE, okay, and this is EH. EH is EC plus, I mean, EC minus 3KT, right? This is what was asked in the question. EC minus KT, the probability of state being filled by an electron at this energy, and EC minus 3KT of probability being the state being filled by a hole at this energy. So now we should equate the two, right? Uh, Obviously, after substituting E equal to this in this and EH equal to this in this, we'll get following. Do this along, okay? And just if you are able to, I mean, finish this question before me, type in chat A, B, C, or D, okay? Because instead of waiting for you to solve and then me solving that again, that would be time consuming, right? So let's do it parallelly. You guys should solve it with me and preferably before me. So this would be 1 by 1 plus, right? I'm writing this expression plus exponential of, instead of EE, we will use this. So this is EC minus KT minus EF by KT. This is equal to 1 by 1 plus exponential of, now this time it is EF minus EC plus 3KT. You all would agree with this, right? So then if you take, what should I say, ln on both sides, I mean, see, if this is equal to this, then these exponential factors are equal, right? And if you take ln on those exponential factors, you would be left with this. You'll be left with this, the argument of exponential factors, EC minus KT minus EF by KT, that is equal to EF minus EC minus 3KT whole divided by KT. Right, now some things would cancel, right? For example, KT and KT would go, and we'll get following. We'll get 2 times EC minus 4KT, that is equal to 2EF, right? Yeah, 2EF. So The question is about Fermi level, right? We need to find the location of the Fermi level. So the Fermi level EF should be EC minus 2 kT.
Is it 3 or 4?
Yeah, please go ahead.
2EC minus 2 kT plus 2 kT.
EC minus 2 kT, right? Because I mean, this 2 factor would cancel this 2. So that's why it's EC minus 2 kT. Agreed. Right, this is done. So which option is correct then? This is actually below conduction band edge, right? This is 2 kT below conduction band edge. So option B is correct. This was pretty straightforward, right? So I guess I should go ahead. Again, I planned to show this, but it turns out this is one of the problems that has been asked in the current assignment. So, I mean, I cannot show this problem at least before the deadline passes away. So I'll be skipping this one as well. So now for a certain semiconductor, the density of the states in the conduction and valence bands, they are Gc of E, A times E minus EC, and Gv of E, B times EV minus C respectively, where these A and B, they are non-zero constants. Okay. So you need to assume the Boltzmann distribution for both types of carriers. Consider the reference potential energy level at valence band edge, that is EV equal to 0. EC is the energy at the conduction band edge. If A is equal to 2B, you need to compute the intrinsic Fermi energy at 300 Kelvin. That is your question. Okay, please attempt this and let me know if it's A, B, C, or D. Okay, I guess I gave enough time. So let me solve this myself now. Those of you who are solving it may proceed and continue to solve it and then just type the answer in the chat. Okay, because I need to start this one now. So see, as per this question, we are given following things. Firstly, this Gc of E, that was equal to A times E minus EC, right? And Gv of E, that is given by B times EV minus C, right? I'll write that as well. So my Gv of E, that is equal to B times EV minus E. Fine. Now, see, we were asked to assume Boltzmann distribution for both the types of carriers. So we'll do that, right? So if we use Boltzmann distribution using, and that actually simplifies the matters a lot. Using Boltzmann distribution. By the way, type in chat, what is the other type of distribution if it were not Boltzmann distribution? If we were not told to assume Boltzmann distribution, then we had to use which distribution? Just type that in chat. Okay, I'll proceed and continue it. If at any point of time the question is not clear, let me know. Just type repeat the question and I'll repeat it all over again. So since we're asked to assume the Boltzmann distribution, we'll assume that and we'll have this Fe of E. What is the Boltzmann distribution? It's negative exponential of that, right? See, this is exponential of minus E minus EF by KT. FH of E, that is approximately minus EF minus E by KT. What have I done actually? In that Fermi-Dirac distribution, if you ignore 1 in the denominator, right, and only consider the exponential part in the denominator, you'll get this, you'll arrive at this. Okay, neglect 1 in the denominator in the Fermi-Dirac distribution, you will arrive at the Boltzmann distribution. So what is then n? We know that n is equal to integral EC to infinity GC of E FE of E dE, right? And that is equal to integral EC to infinity A times E minus EC exponential of minus E minus EF by KT dE. So this implies that n is equal to integral EC to infinity A times E minus EC exponential of minus E minus EC plus EC minus EF whole divided by KT dE. Right. Then if you separate the exponential factors, you will get following. Right. I mean, I'll be splitting this exponential factors into two. So this is A. I mean, this and let me just write this first. Exponential of minus EC minus EF over KT, and then integral EC to infinity E minus EC exponential of minus E minus EC by KT dE. Just check it quickly if that adds up or not. Right, simple. I mean, I just took out an I split the exponential factors into these two, right? And it turns out this exponential factor did not had any E dependence, right? It only depended upon EC, EF, K, and T. So I just took this out of the integral, right? That is essentially what I did in this step. So then I'll make two substitutions. Firstly, I let E minus EC, I let that this by KT, I let that px, uh, which will actually give me that E minus EC is x times KT, right? So what is your DE? Your DE is dx times KT, right? So when your E is equal to EC, what will your x be? When E is EC, your x is 0, right? So uh, x is equals to 0. Similarly, at E is, I guess, infinity. I mean, x will still be infinity, right? Because if this is very large, you can just ignore this off and x would be infinity. So now what? If we make these substitutions into this equation, we'll get following. I'll just change the color notation. This would imply that n is equal to a, this pre-exponential factor EF minus EC by KT, integral 0 to infinity x KT exponential minus x dx KT, right? This implies n is equal to a KT squared exponential of EF minus EC over KT, integral 0 to infinity x e power minus x dx, right? Likewise, we can just put this as equation, I guess 1. Similarly, you can see, you can start for holes, right? You will start for holes with this, like we started for electrons, right? And end up at an equivalent, corresponding equation for holes. I mean, you will start with this. I mean, I'll be leaving this as homework for you. You will work it out. Firstly, I'll write the equation from which we need to start. From minus infinity all the way till valence band edge EV, GV of E, FH of E, DE, right? And yeah, just work this out. Let me write this. This is your homework. And you'll arrive at this equation that your P is equal to some, the B factor, right? Because you do have a B factor here in GV of E. B KT squared, your exponential of EV minus EF by KT, right? So this would be your 2. How this equation 2 comes, you guys would solve it. Okay. And then again, we would use a substitution and that your y. Yeah, wait, I'll write this. You'll write that your y, that is equal to EV minus EF by KT. Right, if you do that, and just a second. I mean, my bad, I guess I missed out. I mean, we need to use this substitution somewhere here, right? In this homework. And what we'll end up is we'll getting we'll be getting this one as well. There would be this factor, right? There would be this factor 0 to infinity. I guess I should stick with the color though. Right? 0 to infinity. Y. Why is it not moving? This is y exponential of minus y and yeah, dy, where your y is given by this one. Simple. This is your equation 2. How this comes, you'll work it out. This is pretty similar, right? Just follow identical corresponding approach here. Now, n equal to p equal to ni, ef is equal to efi. Now now when n is equal to p is equal to ni, your ef and your ef is equal to intrinsic Fermi level EFI. And if you use the first and second equation, right, these two equations will arrive at following. I mean, basically I'll be equating the two. If you'll equate the two, you'll get this 2b. I'm skipping steps again. Okay, you just need to use pen and paper to validate them. 2b exponential of EFI minus EC by KT, that is equal to b exponential of EV minus EFI by KT. So that gives us this one, which means, I mean, B and B would cancel out, right? B and B won't be there now. We'll be left with, and I mean, let's take this exponential here. This would be exponential of EFI minus EC minus EV plus EFI all divided by KT, right? That is equal to 1. Now, if you apply ln on both sides, what would happen? You'll get this, you get the following, right? I mean, let me take this 2 first here in the denominator and then apply ln. I'll get following 2 EFI minus EC minus EV all divided by KT, that is equals to ln of 1/2, right? And yeah, then it's manipulation, right? This is EFI. You can express that as EC plus EV whole divided by 2 plus KT ln of half. But since EV would be 0 in this case, right? I guess I will use a different page, right? Uh, your EV is equal to 0. So what are we left with? Your EFI would be equal to EC by 2 plus KT by 2 ln of half. And then you just need to, plug in the values, right? For example, KT is something that you know. Why? Because T is provided, right? You are given that this is you. We took EV equal to 0, right? Now A is equal to 2B. I guess I have already used it. Yeah. What else do we have info? Actually, that's pretty much what we need. We need to express it in terms of EC. I was thinking how to eliminate EC, but yeah, in all the options, EC is present, right? So I need not eliminate EC. So this would be, sorry, just a second, battery is low. Yeah, again, uh, I hope it's audible again. So actually the battery was low, that's why I plugged in the charger. So now where were we? Yeah, I mean, let me plug in the values now. Your EFI would be equal to your EC by 2 plus this would be KT is at room temperature, it's 26 milli electron volt, right? So this is 26 milli electron volt whole divided by 2 factor, and then it is ln of 1 over 2, right? And your EFI, that is equal to EC over 2 plus, mine's, this would be 9.01 milli electron volt, right? So which option is correct? It's option A, right? So option A is correct. What about this one now? Question number 7. Please try this out. We need to consider a semiconductor that is in thermal equilibrium, right? That is no current. And we need to assume that the donor concentration that varies as this, the expression for ND as a function of x is n0 exponential of minus 10x, right? Exponential decaying doping over this range, right? 0 to zero point 0.1 meter. When x is lies in this range. And yes, given that n0 is some constant, and we need to assume that this temperature is the room temperature, 300 Kelvin, and we need to find what is the value of this electric field. Okay, that is essentially what the question is. So let me find this. You guys can attempt it. I'll do it at my end as well. So this is, I know that J total, that is equal to J drift plus J diffusion, right? So what is your I total current? Current is basically J drift times area, right? Or what I could say is I wrote this J total as I total by A and then took A on the other side. So this would be J drift times your this area A plus J diffusion times this area A. I guess I should use red. So that's how you would understand it. Fine. But now at equilibrium, which of these quantity is zero? At equilibrium, this I total would be zero, right? Because it is given that the semiconductor is in thermal equilibrium. That is no current is sorry, I total that is equal to zero. This is something that is given. So if that is the case, then I can write zero that is equals to the expression for the drift current, that is Q mu n n e plus q dn dn over dx, right? And I'm given following things, right? I've been given n is my n0 exponential of minus 10x. So what should be dn over dx? Dn over dx should be minus 10 n0 exponential of minus 10x, right? This is what dn by dx would be. I guess we need a page. So yeah, if you plug this here, you'll get following. You'll get Q mu n n e plus Q dn minus 10 n0 e to the power minus 10x. You'll get that this quantity is zero. But remember, what is this? This is nothing but your n, right? So I'll replace this by n. Let me do that. So this would be Q mu n n e minus 10 Q dn n. That is equal to 0. So which implies that your this electric field, right? Which implies that your electric field E is equal to 10 times dn over mu n, right? This is what your electric field would be. Now, what is dn over mu n? We need to solve this, right? We need to compute the numerical value. What is dn over mu n? These quantities dn over mu n, dp over mu p, you should try to remember these because they would come in handy, especially in solving problems on, I mean, such kind of problems on carrier concentration, doping, and other similar related problems. So dn by mu n is, just a second, your dn by mu n is kT over q, right? So why don't we write, and since the temperature is 300 Kelvin, right? Sorry, I confused dn by mu n with dn. That's why I was telling you to, I mean, you should know the quantities. See, this is nothing but kT by q. And we know kT by q is 26 millivolt, right? This is 26 millivolt. at 300 Kelvin, isn't it? So your electric field, I mean, you can plug in the values. Your electric field E, that is equal to 0.26 volt per meter. Right, so which option is correct? It is option C, right? Option C is the correct one. Okay, now the next one. This is actually simple. You're having three scattering mechanisms present in particular semiconductor material, and if only the first scattering mechanism were present, the mobility would be mu1, that is given by 2000 centimeters square per volt second. Right, and if only the second mechanism were present, the mobility would be mu2, that is given by 1500 centimeters square per volt second. Right, and similarly, if only third were present, the mu3 would be given by 500 centimeters square per volt second. Then what should be the net mobility? I mean, you would simply use the Matheson's rule, that 1 by mu total is equal to 1 by mu1 plus 1 by mu2 plus 1 by mu3. So which is your 1 by 2000. I mean, let's express this throughout in terms of the centimeter square per volt second units, because we need to express the final mobility in centimeter square per volt second only. So let's not change the units. 1 by 2000 by 1 by 1500 plus 1 by 500, right? So which is 1 by 500 into 1 by 4 plus 1 by 3 plus 1, right? So this implies that your mu total is given by 1 by 500 multiplied by 19 over 12, right? 4 3s are 12 and 3 plus 4 is 7. Wait, 3 plus 4 is 7, 7 plus 12 is 19. Yeah, this is 19 by 12. So your mu total would be equal to 315.8 centimeter square per volt second. So this the answer that is correct is option A. Okay, I mean, please attempt this question 9 now. You need to assume that silicon with band gap Eg equal to 1.12 electron volt is under equilibrium. So now if the whole concentration is 1E15 per centimeter cube, then what is the electron concentration? Pretty simple, right? We are given that the equilibrium is established. So we would use the law of mass action, right? So if we use the law of mass action, which is Np equal to Ni squared, right? And since the whole concentration is already given, what is whole concentration? Whole concentration is 1 into 10 to the power 15 per centimeter cube. So what is N now? N is given by Ni squared by P, right? And what is your Ni? Ni is 10 to the power 10, right? 10 to the power 10 per centimeter cube. And if we squared that, we'll get 10 to the power 20, right? Whole divided by P, and P is your 1 into 10 to the power 15, right? So what is your N now? Your N is 10 to the power 5 per centimeter cube, right? This is your N. So the option that is correct is option C. Fine. So we are done with the ninth one as well. Again, 10th is a question that is actually being asked in your present current assignment. I mean, whose deadline is not yet over. So I won't be able to show this one in this session. So I'll move on to the next one. Now we'll be having some very short type questions, right? I'll only take, I mean, if you'll interact fast, we can just end this session within 15 minutes. Up to you. So please be alert and interact as soon as possible in the chat, and we'll be finishing this session as soon as possible. So now a piece of silicon, it is doped with 10 to the power 16 per centimeter cube of aluminium. Okay, so aluminium doping is used. So by the way, is aluminium acceptor type doping or donor type doping? Is it donor dopant or acceptor dopant? It is acceptor dopant, right? And what you need to do is you need to determine the position of the Fermi level with reference to the intrinsic Fermi level, right? So let's see how we'll approach this. So we are given that P that is equal to Na that is equal to 10 to the power 16 per centimeter cube, right? But we know from the equations that we learned that P is also given by Ni exponential of Ei minus Ef over Kt, right? So what is then Ei minus Ef? Your Ei minus Ef should then be Kt ln of P by Ni, right? And yeah, then I'll be just plugging the values then. So your Ei minus Ef should be equal to Kt ln of your P is this, right? And your and see, we are given that we need to take Ni as 1.5 into 10 to the power 10. So I'll do the same. I'll write 1.5 into 10 to the power 10. Then what is now your Ei minus Ef then? Your Ei minus Ef, if you'll work it out, this should come as 0.3469 electron volt. Is this fine? So now, again, a short type question. Which of the following statements is true for density of states? See, this one is not numerical, so this is theoretical one. And since I'm assuming all of you would have already seen the lectures, you should be able to answer this. So which statement is true? Could you please type in chat? Is it A, B, C, or D? C, it represents number of states per unit volume in a semiconductor. Well, it is a function of energy and not area volume. Just a second now. This is no. I mean, I guess you are confusing. I mean, there is a slight confusion. This should be per unit energy per unit volume, right? Because as per the definition of density of states is, I mean, per unit energy per unit volume. So that is the reason why we will discard this option C. Is that fine, Shiva? So then which option should be correct? Should be option D, right? Because it does depend upon the dimensionality of the semiconductor. Why? Because we saw in the brief recap lecture that as we change the dimensions, the density of states expression changes, right? So that is the reason we'll go with option D, right? If any of you has any doubt, he can revisit the lectures that Professor Sanjeev Sambandan has taught, and I mean, the doubt should be addressed. Try to revise as much as possible and take notes. So I guess I should mark this as this is something that is self-explanatory. What about this one? You need to select the most appropriate option in the intrinsic semiconductors. What is the most appropriate one? Can in fact someone unmute and let's have a discussion on this one. There are 3 students in the meeting, and I'll assume all 3 of you are serious because you are still hanging in there. So can anyone unmute and let me know?
Okay.
Yes, Shiva, please go ahead. So what do you think is the correct option among these?
So Na square is equal to N is equal to P, and in thermal equilibrium there will be same number of electrons in conduction band equal to the same number of holes in valence band.
So you are saying that the concentration of electrons and holes should be same in this intrinsic semiconductor, right?
Yeah.
Yeah, I
In
agree. That is the case. But what about the second option? Why would you discard this one? That the Fermi level is in the middle? Shouldn't
that
that
will
be
be
case?
depends on the effective mass of
Correct, 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 correct.
electron and
Because we already saw that problem, right?
yes,
Unless we'll have same hole and electron effective masses, the Fermi level won't be in the middle, right? I appreciate. That was good answer. So as I mean, I need not explain it again. He already explained it. So the correct answer is option A. The concentration of electrons is equal to concentration of holes in the semiconductor. We cannot go with Fermi level in the middle option because that is something that requires a condition, right? Effective mass of holes should be equal to effective mass of electrons. And since we were not given that, we cannot just assume anything. Now, with that, we'll go to the uh, next question now. We are left with 2 more questions. Again, objective type. Just a second, why is this hanging? Okay, so what is freeze out? Would you like to answer this as well, Shiva? Because I'm assuming only you are the person that's having mic among the 3.
yes sir, but I'm little bit confusing.
Okay, if I give you hint, can you answer this? What about now? Which region is the freeze out one?
Reservoir that
Okay, let me help you out. A, B, or C? Which one is freeze out?
B I think.
The correct answer is A. Why? Because freeze out is the region where
At low
the
temperature
mobile
that
carriers are very less in the extrinsic semiconductor because the temperature is very low, right? Freeze out. In fact, the word itself suggests, right? Low temperature region, freeze out. So that's why the correct answer is this B. So now what about the last one for the today's session? In a p-type material, what happens to the Fermi level with temperature? As we increase the temperature, how does it vary? Okay, I mean, proceed step by step. Where is the Fermi level located in a p-type semiconductor?
near to valence band.
Near the valence band. So it's below the intrinsic level, right? Below the Eg by 2
It,
level,
it,
right? So as the temperature increases, what happens?
as temperature for electron hole pair is created.
Yeah, I mean, the free electron concentration increases. See, the idea is as the temperature increases, the Fermi level reaches the intrinsic level, right?
Yes.
So it increases. Had it been the other way around, okay, I guess I should not touch that one. Probably that is one of your assignment questions. So the thing is, option C is the correct one, right? 15th. I guess with that, we can wind up today's session. We solved many questions today, although it's only 1 hour, 15 minutes, but still, I guess this much is fine. So thanks for tuning in. And yeah, I forgot Shiva. I mean, at the beginning of this session, you had told me that there is, some question regarding this week two, right?
It's a two questions are
Yeah,
I
but
think
that
my
question is from the current set of questions, right? I had not shown in this one, right?
I no.
Actually, your voice is, barely audible. Could you
Is
please?
it audible? No.
Yeah, it's much better now. It's much better now.
Okay. Actually, this week two questions, week two
Yeah,
assignment, the
yeah,
deadline is over and answers came. But
okay.
I'm thinking that there is two answers they have given wrong. Can I
Two answers
share?
have it given a wrong. Okay. See, actually, I did not bring
I
the
can
current set
share.
of question. Can you share it? Yeah, yeah, please go ahead. Share it.
I can
It's
share.
fine. Yeah, in fact, other peoples can also, other students can also look into this because anyway, this is being recorded. So they will also get to know this.
Am I? Is it,
Yeah, 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 it's visible. It's visible.
okay. The first question has the answer that he has taken the wrong Avogadro number and he got the answer 26, sir.
Fine. He
Atomic
took
number.
wrong Avogadro number. Fine. So what is the issue then?
Then the 26 number has equal to iron, I think, atomic number.
Okay, I understood probably your
Okay.
question.
The second question is the what is the actual metal if he correct the Avogadro number? Even if he correct the Avogadro number, the accepted answer is iron. How can the wrong he taken the wrong Avogadro number and got the iron, and he has taken the right Avogadro number and he also got the right answer? Is it same answer?
Fine,
I
as
got
far as I understood, you are saying that if he takes this wrong Avogadro number, he should get iron, right? That is what you are saying.
yes,
Okay,
and
fine. I
the
guess,
answer also
it's fine. What you can do is just write this on forum, okay? Just write it and describe this in detail. What is the exact issue? And I'm sure this would be reevaluated. And many questions go for evaluation. So
and
just
other
don't
one
worry. If you are
second this one
confident, yeah, yeah, please.
and this one also
Mm-hmm.
n lambda is equal to 2d sin theta. We project the like that electromagnetic wave so that the output has to be constructing wave, right?
Mm-hmm.
It has to be constructing wave so that we will change the angle. It should be constructing for different number of n, different values of n.
Fine.
So
You need to.
they asked that what is the maximum possible Bragg angle. So we have to change the n, change the number of n, the value of n, so that
Mm-hmm.
at that value that maximum possible angle should come. But answer given is 8.63. This is the minimum Bragg's angle. Actually, it's coming. It
Okay.
0.5 2d is equal to 1.
I understood. I understood. Is there any other question apart from this one?
And I got week one, sir. Actually, I mailed you 4, 5, 6.
Yeah,
Fourth one,
you had.
you have actually you solved it in the same lookalike problem in
Okay. So that one
assignment.
is fine, right?
That
Is
one
that
is
one
fine.
fine?
So
Okay.
fifth and sixth, I researched on several books and I tried it. So I got wrong answer. Do other people also got the same answer, or their answers also wrong or not? What
Just tell
happened?
me one thing. Do you guys communicate on, forum or anything else? There
No, sir.
should
I
be a
actually I
discussion there.
yes, yes.
Why is
I
discussion not happening?
I don't know, sir. Even I started one discussion, no one answered, and I answered other
That
one.
is bad. That is bad.
And
If he had raised a query, even if the TA had not, I mean, I'm not the TA actually assigned to look into that, but I'll still do my best. I'll go through the queries again. But you guys, all of you should have a discussion. If some student is raising a point, just look into it, because only if there is, I mean, indeed some problem, if, I mean, if you want that to be considered for evaluation, you guys need to, I mean, raise a point, unless you guys disagree with that. If you guys disagree, just write your opinion, but do communicate. I mean, not having a discussion on a forum doesn't make sense, right? Because, I mean, that invalidates the purpose of the forum itself. So yeah, I mean, I'll
and
look into it, Shiva. Fine. I
okay,
mean,
sir.
do one thing,
And,
raise this as well on the forum. Okay.
and
I'll
out and which forum, sir? In the discussion forum.
discussion forum. Yeah, there should be one discussion forum, right?
Yes, yes, there is.
Yeah, yeah, yeah. Just raise it there.
Or is there
And
any feedback form for assignment also?
feedback for the assignment should be, I guess. I mean,
There is
there is
no.
one feedback for the live interactive session, but that is different. I mean, in that feedback, you need to provide the feedback regarding the questions that were taught in live interactive session. And
Yes,
in
sir.
fact, we have been strictly, I mean, advised that you cannot show a question that is, I mean, at least not before the deadline. Those are some guidelines that are made pretty straightforward. So that is the reason you might have noticed we avoid the questions that are being asked in the current assignment, especially before the deadline. So we'll do one thing. You raise this on the forum again and mail it to me again as well, at least for the week 2. Week 1, I already have your mail. So I'll also communicate it at my end to the NPTEL team if possible. But do raise this on forum itself, because we are told that this query, I mean, any such queries, they should be raised on forum. Okay,
Okay.
fine. Thank you. Is there anything else?
No, sir.
Thank you, thank you, thank you. So yeah, let's wind this session up then. Okay, bye bye. Thank you.